All right, let's get into it. Today, we are tackling a seriously weird physics puzzle, one that popped up around the turn of the 20th century and got so strange, it forced us to literally rewrite the rules of reality itself. So, right out of the gate, here's the core mystery. Think about it. If you shine a super bright, intense red light on a piece of metal, nothing happens. But then, you take this dim, faint little violet light, and boom, electrons start flying off instantly. How does that make any sense? You'd think more power, more brightness would do the job, but nope. To figure this out, we have to go back to the scene of the crime, which was this deceptively simple experiment. All scientists were doing was shining light onto metal plates, just to see what would happen. And what they found, well, it was anything but simple. Now, this whole thing has a pretty straightforward name, the photoelectric effect. Photo for light, and electric for the electrons getting kicked out. You shine a light, you get an electron. Sounds simple, right? As it turns out, the rules of this game were just incredibly strange. And this is where everything just completely fell apart for classical physics. See, for more than 100 years, everyone knew light was a wave. So a brighter light means a bigger, more powerful wave, which should blast electrons out with a ton more speed. But that's not what happened. A brighter light knocked out more electrons, sure, but it didn't make them any faster. And even weirder, if the light was the wrong color, like red, you could make it as blindingly bright as you wanted and absolutely nothing would happen. And get this, the whole thing was instantaneous. There was no delay, no time for energy to build up. The old rules weren't just bent, they were completely shattered. So the old theory was just broken. To solve this puzzle, physics needed a completely new, totally radical way of thinking about light itself. I mean, think about it. The wave theory of light was a pillar of physics, and it had just failed, spectacularly. This was a full-blown crisis. And into this crisis stepped a revolutionary new idea. So, say hello to the photon. The idea here, first cooked up by Max Planck and then really pushed forward by Albert Einstein, was that light isn't some continuous flowing wave. It's actually a stream of tiny individual packets of energy, like little bullets. Each one of these packets is called a quantum. And when we're talking about light, we call this quantum a photon. And here is the secret sauce, the key to the whole thing. A photon's energy has nothing to do with brightness. It's all about its frequency, which is what our eyes see as color. So a high-frequency violet photon is a high-energy particle. A low-frequency red photon, that's a low-energy one. It's that simple. Okay, so now we have this crazy idea of light bullets. A young Albert Einstein takes this concept, aims it squarely at the photoelectric puzzle, and in 1905, he just completely cracks the case. So first, Einstein says, let's think about the metal. It has a property he called the work function. The absolute best way to think about this is like an exit fee. Every single electron is stuck to the metal, and to get out, it has to pay a very specific minimum energy cost. And the whole thing works like a simple one-on-one deal. A single photon shows up, hits a single electron, and gives it all of its energy. The electron immediately uses part of that energy to pay the exit fee. That's the work function. And whatever energy is left over, that becomes the electron's speed, its kinetic energy, as it zips away. And just like that, this photon model explains everything perfectly. Why does a certain color not work? Well, because that low-energy red photon just doesn't have enough cash to pay the exit fee. Why doesn't making the light brighter make the electrons faster? Because brightness just means you're sending more photons, not higher energy ones. It's like getting pelted with a bunch of ping pong balls instead of one cannonball. And why is it instant? Because it's a direct, one-on-one collision. There's no waiting around. The puzzle was completely solved. But of course, in science, solving one puzzle just opens up an even bigger, deeper one. If light, which we all knew was a wave, could suddenly act like a particle, what else could be true? This became known as wave-particle duality. Light isn't just a wave, and it's not just a particle. It is somehow, fundamentally, both things at the exact same time. And which one you see just depends on how you decide to look at it. And that, of course, led to a really mind-bending question. Okay, so if this thing we always thought was a wave can pretend to be a particle, could it work the other way around? Could things we think of as solid little particles like electrons sometimes act like waves? Well, in 1924, a physicist named Louis de Broglie just went for it. He said, yes, they can. He came up with the wild hypothesis that all matter, every electron, every atom, even you and me, has a wave nature. And as crazy as it sounded, experiments later proved him right. They fired electrons through tiny little slits and watched them create interference patterns on the other side, something that was supposed to be only for waves. Now, I know this all might sound like some pretty abstract, out there physics, but these bizarre quantum rules are actually the foundation for so much of the technology that powers our world today. I mean, take solar cells. They're basically giant photoelectric devices, using photons from the sun to knock electrons loose and make electricity. You know the sensor on an automatic door that opens when you walk up to it? That's the photoelectric effect. It's detecting when you break a beam of light. And the image sensor inside your phone? It's just a huge grid of millions of tiny light detectors, each one capturing photons to build the picture you see. But maybe one of the coolest applications comes from flipping the idea around, not from light acting like a particle, but from a particle acting like a wave. And that's the electron microscope. You see, by treating electrons like waves, we can take advantage of their incredibly short wavelengths. We're talking up to 10,000 times shorter than the wavelength of visible light. And because of that, electron microscopes let us see things in way more detail than any light microscope ever could. We're talking about seeing the actual structure of viruses and even individual atoms. So if you take one thing away from all of this, it's this. The universe, when you get right down to it, is a really strange and kind of beautiful place. That neat little line we like to draw between waves and particles, it just doesn't exist. It's all a blend of both. And that leaves us with one final, pretty profound thought. If the fundamental building blocks of everything, all the electrons and photons that make up our world, live in this weird, blurry state of being both a particle and a wave, what does that say about the solid, definite reality that we think we see around us every single day?